All right. So is there anybody here who's still registered for both courses? I think for both 1051 and 1068. Yeah. Yep. Saw you this morning. Okay. All right. So, and I know I saw a lot of students were registered for both earlier to begin with.
What courses?
1051 and 1068 was redundant to register for both. But it seems
I only have one in my schedule. It's this one.
That's good. Fine. All right. So we have. So welcome to introduction to. Sorry. Well, let's see. I think the program is typically called program design and abstraction, but it is introduction to Java programming, pretty much. All right. Let's see if I can. There we go. That's slightly better. All right. So, how many of you have any programming experience?
I took a Java class during high school.
Okay, that's good. And where did my projector go? Anyone else? And is everybody here in the CIS program? So everybody here is a CIS major, yes? Nope. You are?
I am.
You're. Okay. Yeah, that's fine. Okay. You might find that that 1051 might be better suited for your taste, but that it also depends on what you intend to do. This class is intended for people who want to go into 2168 next, the data structures class. So if that's what you want to do, then that's more than fine. I've got a number of students who are in 1051 who are, and I'm teaching that as under the assumption that basically that course is going to be the only programming course that a lot of people take. There. Okay, there we go. And for yes.
Sorry, I was just wondering, is 1051 a prerequisite for CIS majors or no?
So that's a very interesting question. It is going to be in the fall. But anybody who's taken this course, it's not really going to matter. So when did my projector cut out? Let's see. This is input A. Oh, this is embarrassing. Okay. It was working. It was working like 30 seconds ago. Sorry about this. All right. So while I'm getting this, trying to figure out why this isn't working. So have you all had the chance to check out the syllabus video? So as you all checked out Canvas? Yeah. Right. So I posted a playlist on there, and I posted my a video on this where I go over the basics of the syllabus for the course. I've also posted the syllabus online. I expect you to read it at some point. So, and I'm not going to waste too much time by going over it in class. The main thing to know is that you're going to get the majority of your grade by demoing your work to me. That might be doing it. By demoing your work to me in class or during my office hours. My office hours are basically going to be on Wednesday, so from 1 to 3, so you can stop in at any time and meet me there. And if you can't make it to office hours for some reason, then you can email me, and I'm pretty much available to meet anytime on Wednesday. Otherwise, I can meet you online via Google Hangouts pretty much anytime. All right, so textbooks for this class, you may have had trouble finding them. That's okay, because they're free. So I'm using 2 textbooks. Think Java is the primary textbook that we'll be going off of. You can download it for free online. You can also buy a hardcover copy. I figured that you probably don't need to spend any more money on textbooks right now, considering, tuition is already expensive enough. And it's a fairly good textbook.
how would I download it?
So you can go to it by so there's a link provided in the syllabus, but you can go to Think Java. And there's this website. You can order it from Amazon. You can also download the PDF here. You can also they've also got an HTML version that you can read online, and then there's an interactive version right over here, which is actually pretty nice because it will, everything is nice and formatted, but also it's got the ability to like run code in the browser for you, so you can watch what happens as code gets executed in certain areas. So that's pretty cool. So it's a fairly robust textbook, and I've also listed a second textbook on our syllabus, which you can find right here. So I'm getting a weird sense of deja vu because I've kind of done this class already. I just did it for Python in the morning. So, all right. So, right. And then I have another one here that with a link in the syllabus that you can click on, and it is the Introduction to Programming Using Java. And again, you can download a PDF of the textbook. Here, I don't know if this one's available in print, but you can download a PDF, and this one's quite large. It's 800 pages, but it is quite, quite extensive as to what it handles. So now this is a very small class, so that does a couple things. But the primary thing it does is that it enables me to spend more one-on-one time with each of you and make sure that we move forward. There are 3 homeworks posted online, and one of them will probably be done in about 15 minutes in class here. So another one is fairly simple and just takes some because it's more of an art thing, and that one won't take too much time for you. And then the last one, I'll give you some time to work on that, but we'll see. But you'll see that the 3 homeworks that I'm providing to you all at once isn't really going to be too much. One of these 3-hour sections is going to be I'm aiming to be about a week's worth of class, if not like 3/4 of a week's worth of class on that you would normally get during a regular semester, and that seems a bit intense. So let me tell you about why this is going to work, about how this is going to work. First, I'm recording any lecturing that I'm doing in class, such as this right here. So these lectures will be available for you in a playlist on YouTube, and you can find that on Canvas by going to by logging onto the course. Okay, you go to the course, you log in, and you click on our course, and if you go to Pages, there's class code, which is where I'll upload the code from class as we work on it, and then here's access to a playlist, and you can click on the playlist over here. And I did this syllabus for both the sections because really the syllabi are pretty much the same, so no problem there. And then, I'll upload the videos after class and make so that you guys have the ability to watch them again. The next thing is that I'm hoping by next week I can start providing videos for you to watch outside of classroom. So rather than doing a lot of homework in class, outside of the classroom where I'm not there to help you work on it, a lot of the time you should be working on homework in class where I can help you and help you get it completed within the allotted time. So there should be a lot more time done in class. Provided for you to work on stuff. Also, because it's a small class, I'll have the ability to deal with each of you individually. Doing your homework is kind of essential, even if it's late. Homework is if your homework is late, it's going to be 5% per day, so that's not 5 points off. That's 5%. So it's a cumulative kind of deal. So first day is a 95. Second day is a 90.25, and so on and so forth. So 5% minus 5%. So So you never lose all of it, and the maximum and the minimum you can score on something. Sorry, the most I'll take off is half. So you can always get half credit in case you like fall, off the earth for basically a week or two, and then decide not to do that. But I suggest not doing that because the course is only 8 weeks long. I have a syllabus. Sorry, I have a schedule of sorts. Okay. I don't expect it to survive the first 2 weeks of class because it's just very tentative. But it gives me an idea of all the stuff. But it gives you an idea of all the stuff I want to cover. I have a feeling we're going to be covering stuff faster. Okay. So that's enough of me prattling on. So let's go ahead and talk about what this course is intended to do. It's intended to get you to think like a computer scientist, and it's intended to get you programming. To think like a computer scientist really just means you need a problem. It means that we're going to learn how to problem solve in this class. As I went over in 1051, computer science is not the study of computers. It's not the study of computers in the same way that astronomy is not telescope science, right? And biology is not microscope science. Computer science is just poorly named. In other countries, it's called informatics, which is also a weird name, but maybe it's a bit better. The idea here is that computer science is to teach you how to do problem solving. Computer science is the study of algorithms. So that leads us to the question of what is an algorithm. Algorithms are what we are essentially, if you've ever followed a recipe for cooking something, an algorithm is just that. It is essentially a recipe for solving a problem. Algorithms are well ordered, meaning that algorithms follow step-by-step and are step-by-step instructions. One always occurs in front of the other, as you'll see, and they are unambiguous, meaning that in language there's a lot of ambiguity. When I tell you to do that, there's a lot of different things that could mean, and it's a lot of stuff that can be lost in translation, and we can't afford that with computers. Computers don't deal with ambiguity at all. And they will always do something. Okay, so we'll go over just the slightest bit of history before we get, and then we're going to work on getting Java up and running on all your computers. Familiar, yeah? Exact same format as the 1051, right?
I don't think I might have room on my computer.
On your computer. Okay, so that we will address that. So has everybody brought a laptop to class? Okay. No? Do you have a laptop? I do. But it's at home. Okay. So is it one you can rely on? Like you can use it, you can get it working, it's not slow? Okay. Okay. So don't worry for right now. We'll get it set up on Thursday, but we'll want to make sure that you can program in Java. You need about 200 megabytes worth of space on your computer.
200 megabytes?
Mm-hmm.
I might have that much.
So
I think I have like 4 gigabytes.
I'll work it out with you. Okay. So there's a lot of so I can go through stuff with you, but it's important that you basically be able to program on your own computer, because I don't know, because while we could possibly get it working on these computers, it's a pain in the neck to get for the IT people, and you really should be able to program on your own machine anywhere, and it makes it easy for you to come to my lab and show me your work and make small changes, or office hours rather. So we'll do history, then we'll get started on your first program on your computers. Okay, so this is a very brief history of computer science. It's actually nowhere near a complete history of computer science. And it is kind of it's kind of a very, very brief history. So we might as well start. We have to start somewhere, and the starting point I look at is the abacus, which is not even a computer. It's just data storage. For the longest time, we didn't really have anything that can do things automatically, which is really kind of the central question of computer science, is that how do I automate things? What can I automate them? how can I automate them efficiently? And what do we even define by efficiently? Classically we define efficiency by basically taking the least amount of time, but more and more we because we're carrying around these little battery-powered computers in our pocket all the time, sometimes efficient means maybe it's okay for it to take a little longer if it saves some energy, if it uses less energy. So there's that kind of cost-benefit analysis. Abacuses. They're not computers. They're little things with beads on them that you could use to do some basic manipulations on data. They help turn a human into a computer, though, right? Being able to remember numbers and add numbers much more efficiently. Not listed here is basically also is kind of a sideline of computer science that kind of got folded into it, which is cryptography. Which is basically as soon as there were militaries and military orders and very big militaries that you had to send orders to, it became essential that you need to be able to send orders to your generals and your troops, and that if your messenger got intercepted, then your orders couldn't be read, right? So that necessitated the branch called cryptography, which is basically the art of code making. Back in the 300s, the cutting-edge cryptographic method was something called the Caesarean cipher, which was fairly simple. Anywhere there was an A, you would shift it forward 3 letters so that all the A's in the orders would be replaced by D's. All the B's would be shifted 3 letters forward, and they would be replaced by, well, what comes after D? E. So, and so on and so forth. Every letter would be shifted forward by 3 letters, and it would wrap around, right? So a Z would be replaced by C. And just to reverse, and if you got your orders, to reverse it, you would just shift it back 3 letters, and that was all you needed. It's not a very secure cipher, but it worked, especially since, literacy rates in the Roman era were pretty low. And the ability to problem solve, well, you had to be able to read in order to solve that problem, so it cut down on the number of people who could problem solve. So it was fairly efficient, but quickly became out of date. Then we really didn't get into stuff that could be until we couldn't really think about computers in a real sense of the word until about the 16 to 1800s, which is when various scientists and naturalists came up with the idea of gear machines, which basically would be these ideas. They had ideas about these machines that they could rotate gears to do computation. Pascal, Leibniz, Babbage all kind of came up with different variations of this idea. Babbage was the important one because he wanted to create a gear-based machine where basically you could rotate gears, and in that machine, and then they would print out their output on some paper, right? So you didn't have to necessarily read the gears; you could read them. That brings us to Ada Lovelace. Now, Ada Lovelace was the daughter of the poet Lord Byron, but she's known in her own right for being the first programmer. She's as good a person anyway to consider first programmer because she wrote one of the first programs. Babbage had this idea for his analytical engine, which was this gear-based machine, which he designed but wasn't able to produce. The idea was that this analytical engine, the way it would work is that it would take instructions from some punched cards with cards with little holes punched in them, and it would read them in. It would figure out what it would want to compute. And so Ada published a paper, and it showed how she could set the analytical engine to compute these things called Bernoulli numbers, which are these useful numbers in statistics. But not only that, which made her contribution really important, was that she wrote about how the machine that just works with numbers, the analytical engine, could be used for things other than numbers. And that was about 100 years ahead of its time. So computer science really came into in the fold during World War II with the birth of modern cryptography and the birth of modern cryptanalysis. So cryptography, right? Code breaking. Cryptanalysis was cryptography, code making. Cryptanalysis, code breaking. Using machines to break the German ciphers rather than in World War I you could still break ciphers by hand. In World War II, Not so much. How many of you? Pretty much, I'm sure everybody's seen the Imitation Game at some point, right? The movie came out a bit ago, and about Alan Turing and how his team broke the German Enigma ciphers, building a machine to do so. So that data that they collected from that was called Ultra, and that was decisive in the Allied victory. It lowered the war against Germany for about 2 years. With the intelligence for that, and that also branched out into game theory, and all sorts of other interesting things came out of that. Turing, however, is considered the father of modern computer science, not because of the cryptography work and cryptanalysis work that he did, or cryptanalysis work that he did, not and. He came up with something called, his claim to fame is called the Turing machine, which is basically a mathematical definition, a mathematical formulation of a computer. And now that you can have a mathematical model for what a computer is, which he basically without mind going into detail for this class, he basically had the idea that you could represent all information could be represented as a sequence of ones and zeros, okay? And then you can simply take anything that's an algorithm, anything that's a sequence of instructions, and use only 5 actions. If you can encode anything with ones and zeros, then all you need is a long strip of paper that's infinitely long, like ticker tape, evenly divided into a bunch of squares. And you have this moving device that moves along these squares, and it does only 1 of 5 things. It moves left, it moves right, it puts a 0 at a square, it puts a 1 at a square, or it erases what's at the square. That's it. And if that doesn't make too much sense about why this is amazing, that's okay. It's not really mind-blowing until you've taken like a bunch of computer science courses. But he basically formulated that this is all a computer is. And then now that we have it, we can essentially just prove what computers can and can't do. So the first actual mechanical computer, before then computers were people, it was a job. Their jobs were doing calculations. There's no clear first mechanical computer. I put down ENIAC because it's a popular one. It was constructed in 1946. It was made up of a lot of vacuum tubes. It was 1,800 square feet, so probably much, much bigger than the space that you're currently living in. And it was primarily used for artillery calculation. The story since World War II has essentially been only 2 stories for computers. The first is miniaturization, right? IBM introduced the first personal computer, a PC, in 1981. Computers went from being the size of this room to being the size of desks, to being able to sit on a desk, to be able to sit to being able to hide underneath a desk, to being the size of a briefcase that you could carry around with you, to being something you could put inside of a briefcase, to being something you could put inside of a pocket, right? Computers get smaller and smaller. Now they're able to, you can make small little chips that you can put on a computer. That you can put anywhere. The other big thing in computer science is the internet, which is this global system of just computers that are connected to one another. And going on using a computer these days is synonymous with using, applications on the internet, using the World Wide Web, right? The phone is kind of useless without the internet. So the web is so big that the other big applications these days are search engines. You need search engines to be able to figure out what's on the web. All right. So that's kind of your brief introduction to computers, to the history of computers. Programming, though, is just like calculus is only like 3 things that you ever learn in calculus. You learn that all you learn in calculus is limits, derivatives, and integrals. And so that's really all you learn over 3 classes. Limits, you go into a lot of detail. Just like that, computers are made up of like only 3 types of commands. Our book splits it up into 5 aspects. Input. These are the 5 things that make up a program. Input. Reading data. Output. displaying data to the user or creating a file. So you can get input from a keyboard, from a file, from a sensor, from another device. You can get input from somewhere. You can put output at pretty much anywhere that you can figure out how to send data to. So input and output are two things. Doing some math, performing basic operations like addition and division. You don't need to know too much math for this course. Making decisions. So basically going if this, then that. And then the last one is repetition, which is do an action until some point. And pretty much all the programs are made up of some kind of variation of all these 5 things. So what does it make for programming? So what does that mean programming is? You can look at programming as really taking a big problem and breaking it down into small concrete steps that your computer can understand. Okay. So our book defines computer science as the science of algorithms. Algorithms are sequences of steps that specify how you solve a problem. Writing algorithms is a bit of a pain. It's hard not because programming is hard, but because we're human and humans make mistakes, and it's sometimes hard for us to find where mistakes are. But that's a big part of the reason why programming is considered hard. So so the question is, how do you program? Well, you need a programming language to do so. Now, in this class, we're learning Java, which is a high-level programming language. Now, there's low-level programming languages, and we use programming languages because working with zeros and ones, which I did for about 10 minutes which I did for about 15 minutes during a recitation in one lecture years and years ago, was kind of terrible. It took us 15 minutes to do one basic step of adding 2 numbers. It was terrible, and that's why we don't mess with zeros and ones. We mess with words, and because that makes sense for us. Why am I mentioning zeros and ones? Well, computers use bits, binary digits, zeros and ones. Why do they use binary digits as opposed to the base 10 system that we use? Well, because these things are powered by electricity, and using a high voltage and a low voltage is easy to differentiate between the two. So a high voltage and a low voltage, being able to differentiate between an on state and an off state, that's really easy for us to do with computers. So high-level languages, there's a whole lot of them. You've got C, C++, Python, Ruby, JavaScript, and Java. Then there's low-level languages, which are like machine languages. It's instructions that your machine understands. And we're programming in a high-level language because it's so much easier to do so. They're easy to read, and therefore they're easier to write. High-level languages also are portable. When you write a program in Java, you can take it to another computer, compile it, and run it. Or you can take your compiled Java program, and run it anywhere. Java's nice like that. So there's 2 types of high-level languages: interpreted and compiled. And we've got this handy-dandy flowchart here. Interpreted languages, they take your source code, which is the program you write, and they take it line by line and they execute them. And the way it does that is that there's a program written for your computer called an interpreter, and it does exactly what it sounds like. It's like the interpreters who sit at the UN, right? So somebody will say something, and the interpreter speaks, and so and translates it into a different language so that person will understand. And it's pretty efficient. It works because the interpreter is good at its job, but it can be a bit slow. There can be a delay there. Now, our interpreted languages like Python have gotten really good at what they do these days. So there's really not too much of a speed loss for what we'd be doing. And so people like to use interpreted languages for a lot of things. The other solution is compiling. So to take a compiled language is basically to, let's see. Yep. So the idea with a compiled language is that it reads the entire program at once and translates it into machine code, right? So it's the difference between translating something line by line as you get it, right? So somebody's reading their speech at the UN and you're translating it as you hear it. And compiled is you get the entire speech in advance, right? And you translate it and then you hand it to your representative so that they're able to basically read it all at once, right? There's no lag in there because it's already translated, it's ready to go. So Java's weird because it is both interpreted and compiled. It is both. Okay? Instead of translating things into machine languages, it creates bytecode. So what it does is that it kind of fills this space between a programmed language, between an interpreted language and a compiled language, although technically it's compiled. What it does is that it has something called the Java Virtual Machine on your computer. And any program that can run Java, any computer that can run Java has a Java Virtual Machine on it. And it kind of acts like a virtual computer, right? JVM, the Java Virtual Machine. And what it does is it takes your source code, it compiles it into something called bytecode. And then, so it's a two-step process, essentially. You compile your program, and then you execute it through the Java Virtual Machine, right? So as opposed to running an interpreted language. But the advantage of this is that once you compile something into bytecode, you can send it to any computer that runs Java, and you don't have to recompile it. Like if you were working in C, you'd have to compile it once for a Mac, once for a different type of Mac, once for another type of Mac, and then maybe for these machines you'd have to compile them, and then for my machine it'd have its own instructions, so you'd have to compile it once for pretty much every machine. It's a bit of an exaggeration, but you get the idea there. The idea with this is that you compile it once, it runs anywhere on the Java Virtual Machine. So how does that work in action? Well, so let's start by writing Hello World. Now, I'm going to start with basically just using the most basic things I can. I'm going to write a program in my text editor. In a basic text editor. So this is the issue with Java. So let's go ahead and start writing a program. The issue with Java is that is that you kind of have to take it on faith that some things are going to work. rm hello.java. rm hello.java. I've just got to clean up a bit. There we go. Don't have to know about any of these things that I'm doing. So what we typically do is that we open up a text editor of some kind, and I'll show you what kind of tool. And part of this first class is getting you those tools to use. But this is what a program looks like. So we're going to write something called Hello World, which is the first program that we typically write. So your programs in Java look like this. Public class. Here, give me a second. Properties. Let's increase the text size to. There we go. There we go. That's much better. Public class. Hello. So I created a file called hello.java, and it's going to have the same name. And then public static void main string args. And the thing I don't like about Java is that you're going to just have to take it on faith from me that this is how you start a program. This is a bunch of, because of the way Java works, in order to start a program, you just have to basically start it like this. The name of your file, and then we have this thing called the main method, which is where Java looks to begin your program. And now we can start. So this is just basically like formatting and getting things ready so that you can, so that basically your program's a proper Java program. And now here is how we actually can do something. System.out.println. So it says println. And let's just digest this for a second. System, so this is a system command, .out. We'd like to put things out. We'd like to do some output. What kind of output would we like to do? We'd like to print ln, print a line.
So it will show up.
It will show up wherever I tell it to run. So let me go ahead. I'm not going to execute it in here. So but in an IDE, it will show up at the bottom. Here, I'm just kind of showing the two-step process. So I saved it, right? I've saved it on my hard drive. Okay, and now I've got a program, and now I've got to so I wrote the program, and now it's a two-step process. Sorry, I will move this up to the top. Okay. So now the first command is javac. It stands for Java compile. Hello.java. So that compiled my program. It's a very quick process. And what its output is a new file called hello.class. So I took a program and I compiled it. Now we can take a look at hello.class, right? I told you we took the source code, which was this, right? This was the source code. Stuff that you can read even if you don't understand it. And we produced an output file, hello.class, which is a bunch of gibberish. You can see there's a bunch of gibberish. Oh, there's hello world in there, but everything else is a bunch of random gibberish, right? But this is the commands that my program's able to understand. So Java hello. So I just simply say Java hello. I execute the name of the program, and it goes hello world. So that's a two-step process. Now, that can be a bit tedious, as you understand. So what we're going to be using is something called an IDE. Now, there's a lot of different IDEs to use. I use one called IntelliJ to do a lot of my work, but I feel like IntelliJ it's kind of, at least for right now, it's like bringing nuclear weapons to a knife fight. It's a program with a lot of menus and a lot of things on there, so we'll see, right? So, but I'll be using this to program with. At the very beginning, though, we're going to get us set up with something called NetBeans. And the reason for this is that NetBeans can bundle. It will bundle Java together with your the IDE. So you need two things in order to we need essentially two things to be able to program. We need the ability for our computer to run Java. Right? Because I can write a Java program anytime I want, but unless my computer can actually take the instructions and interpret them or compile them, it's not going to really do me any good. So we need to get the ability to download them, and then it would be nice to have an environment where writing Java is easy. So we can go to netbeans.org. You can go to the download page, and over here at the bottom it says. Let's see, Java 8, JDK 8, which means Java version 8, is required for installing and running the Java Standard Edition, Enterprise, and all NetBeans bundles. So you can download it, just the JDK by itself, or you can get the JDK with NetBeans IDE. So click on this link, the second link, and it'll bring you to Oracle's website, which is where you can download it. Accept the license agreement, and select the appropriate one for your computer. Right? If you are running Linux, which you probably are not, then you don't need to follow my directions because you know what you're doing. So how many? I'm sorry. That's okay. I'll be around to help each of you in turn. How many of you have Macs? So one Mac. You have Windows.
Yeah.
Windows. And you have Windows. Okay. For Windows, you should download probably the X64 down here. Okay, I'll be around to you in just a second. So our first and now we'll work on our first assignment in class. Okay? See, we're already at our first homework. So the first homework is as follows. If you look under assignments, it is it's called Someone Famous. Okay? And that one's fairly straightforward. Your assignment is this is just an assignment to confirm that you've got Java running on your machine. You'll install Java on machine, and you'll install either NetBeans or Eclipse. You'll want to create a new file called firstassignment.java. And your job is to recreate My Hello World, except you're going to do something different. You're going to print out a short biography about a computer scientist who is not Alan Turing, who is not Bill Gates, and who's not Steve Jobs. I suggest Googling famous computer scientists, right, and just reading up their Wikipedia article and just printing out 3 lines. Print out each sentence on a separate line. Once you're done with that, there's an extra credit portion to keep you busy while I'm helping other people. Okay? I will be sprinkling bits of extra credit here and there for everybody. So I'm going to start with you, and then I'll move around the room to get everybody set up.
Okay, so this would be a room type, right?
Yep. So you say how much space do you have? 4.2 gigabytes, because you have a very small computer. Right? You've got this is a netbook of some kind.
Hey, so
An Asus netbook. So you've got temporary files. Yeah. Can I see for a second? So this computer. This PC over here. I see. So it is a netbook. Okay. This will make things interesting, I'm sure.
this is a new computer. I don't want anything bad to happen to it.
Don't worry about it. Anything I do won't do with that, but you've got enough space for this. So you'll probably want to download that and install it. And you'll want to delete the file once you're finished installing it. Okay? Make sense?
Delete the file.
Yeah, right. You're downloading it to your downloads directory right now. You'll want to erase it after that. Make sense?
So after I open it, I erase it.
After it's done installing, right? Because this will be going to your downloads directory, right? May I? Yeah. So downloads over here, right? You can.
What about those? I think those are from when I installed Word.
Yeah, you can delete those.
Are you sure?
Yeah.
What's that word?
Yeah. Those are what they are is they're files that download the rest of the They're files that download the install files from the internet. So you're good there. And also with the whole, this thing, you can probably remove the launch of the temporary files as well. So you can remove temporary files as well. Right. So there's some Windows updates and stuff. So once this program is done, which it is, click on it. And then let it run. So it might take a minute to run. And we've already got Eclipse running. So you've got programming experience with Eclipse, or